Hello everyone. Today we're going to be discussing taking the REF and RREF of a matrix. Now, where a matrix comes from when you first learn about this process is you have a system of linear equations. So geometrically this is three planes and we're looking for the intersection point of three planes. You can also think about it as just somebody just gave you three equations that are linear in x, y, and z, and you want to find the solution. Okay, so I have three equations, three unknowns, and so we should expect there should be a unique solution. And as we'll see as we work some examples, that won't always be the case, but it is the case most of the time. So the way you solve this problem is you could manipulate the system of equations by, let's say, adding one equation into the other and trying to solve for x, y, and z. So for example, I might start by getting rid of x by subtracting these two equations. So maybe I take the second equation 2 and subtract it from the first. Okay, or take the first, subtract it from the second. So I get x plus 2y plus z is equal to 8, and then minus x plus y plus z equals 6. And when I subtract these equations, okay, the x's will cancel. I get 2y minus y is y. Z minus z, z cancels as well, and this is equal to 2, so I can actually get y is equal to 2. And then I can plug back in y equals 2 into this system and proceed further by, adding and subtracting equations together. And one thing I can also do is I could have multiplied an equation by a number if that helped me. So for example, if I wanted to get rid of y first, then I could have multiplied equation 1 by 2, and then taken the difference between equation 2 and equation 1. Okay, so that's perfectly valid as well. So I could have instead looked at equation 2 minus 2 times equation 1. Okay, and so this would have given me x plus 2y plus z is equal to 8, and then I would subtract 2x plus 2y plus 2z is equal to 12. And then I could cancel y and manipulate the equations as follows. So I guess where I'm going with this is that in order to solve this system of equations, I have the freedom to add and subtract equations together, and I have the freedom to multiply an equation on both sides by a number. And this is just what we know as algebraically, it keeps the same equalities, right? So if I multiply an equation on both sides by a number, I'm not changing the equation. And if I know two equations are true, then I can subtract and add them together, and they'll remain to be true, okay? So now with this in mind, let's actually write this in matrix form and look at how to do the REF and RREF of a matrix. Okay, so putting this in a matrix form, I'm going to encode the coefficients of x, y, and z. So in this case, my x coefficient on the first equation is 1, y coefficient is 1, z coefficient is 1, and then this is equal to 6, so I write a 6 here. Same thing with the second equation, I'm going to encode it as 1, 2, 1, 8. So 1x plus 2y plus z is equal to 8. And the third equation, similarly, 1x plus 2y plus 2z is equal to 11. Okay. And now I'm essentially going to manipulate this matrix in the same way that I would manipulate these equations and try to get it into a simpler form. What do I mean by simpler form? Well, what I want is by some process of adding and subtracting rows and possibly multiplying by numbers, I want to end up with a matrix of the form 1, 0, 0, 0, 1, 0, 0, 0, 1, and then some numbers x, y, z. Okay, and these are going to be numbers. So we haven't solved the problem yet, so we don't know what they are. But then, once I have this equation, once I have the matrix in this form, I can put it back into the equation form. And if I put this matrix back into the equation form, I could read this off as x is equal to this number, whatever the number is. And then this second row of the matrix tells me that y is equal to some number, and the third row tells me that z is equal to some number, where these are the numbers that I'm getting, okay? So by basically translating this into a matrix, manipulating the matrix via row transformations into this form, and then translating it back into the equation form, I can solve the system of equations. Now the reason why we go through this complicated process is because there's actually an algorithm for translating this matrix into this exact form. And that's what we're going to cover today, okay? So let's begin. Okay, so I'm starting off with 1, 1, 6, 2, 1, 8, 1, 2, 11. Okay. All right, so the algorithm that I'm going to teach you is essentially the following method. So first of all, I want to make sure that this first number in the top left corner is a 1. Okay, so that in this case it's already a 1, and if it wasn't a 1, I would multiply this row by a number to make it 1. Okay, and then once I have a 1 in the top left corner, then I'm going to proceed to eliminate the ones directly beneath it, or not just the ones, but any numbers directly beneath it. I'm going to eliminate those and turn them into zeros. And the methods, the things that I'm allowed to do to manipulate this matrix, I'm allowed to multiply the rows by a number. So let's say I can multiply this row by the number 2, and that would give me 2, 2, 2, 12, 1, 2, 1, 8, 1, 2, 2, 11. Okay? So I can multiply rows by a number, which is the same thing as multiplying an equation on both sides by a number. Okay? Or I can subtract two equations from each other. Okay? So I could, let's say, subtract this equation from this equation. Okay? So that just amounts to subtracting rows of this matrix. Okay, so when I subtract rows, what I'm going to think about doing is multiplying this row by -1 and then adding it into this row. Okay? So when I do that, I'm going to end up with -1 times 1 is -1, added into this 1 is 0. This -1 times 1 is -1, added into the 2 is +1. And then -1 times 1 added into the 1 is 0. -1 times 6 is -6, added into the 8 is 2. Okay? And then I have everything else stays the same. Okay? 1, 2. Okay? All right, so that's kind of nice. And now the next step is actually to get rid of this one. Okay, so I remember I want this number in the top left corner to be a 1, and then I'm going to eliminate everything beneath it in terms of making these numbers 0. So to make this one a 0, I'm going to again multiply this row by -1 and add it into the bottom row. Okay, so everything else will stay the same. I'm only affecting the bottom row when I do this operation. Okay, and so here I have -1 times 1 is -1, added into the 1 is 0. That's what I wanted. -1 times 1 is -1, added into the 2 is 1. I have -1 times 1, -1, added into the 2 is 1. And then I have -1 times 6 is -6, added into the 11 is 5. Okay, great. So let's write that up here. So I have 1, 1, 1, 6, 0, 1, 0, 2, 0, 1, 1, 5. Sorry, my notation with my ones, I'm very indecisive, and so I sometimes write them as, a 1 like this, and sometimes I'll just write it as a line. I apologize for that. Okay, so we're here. Now the next step is I've completed the first step of turning this first number into a 1 and then getting zeros beneath it. Then I'm going to move down the staircase. Okay, so once I've completed that step, I'm going to move down to the staircase and now turn this number into a 1. It's already a 1, so we're good. Don't worry, we're going to cover a more complicated example where this won't be the case in a little bit. Okay, however, so this number is already a 1, so now I'm going to eliminate everything beneath this number and get all zeros beneath it. Okay, so to do that, I'm going to multiply by -1 and add into this row. So I have 1, 1, 1, 6. Then here I have this row stays the same. And then -1 times 1 is -1, added into the 1 is 0 here. These zeros aren't going to be affected. Negative 1 times 0 is 0, added into the 1 is 1. And then 5 here. Oh, not 5, excuse me. So negative 1 times 2 is negative 2, added into the 5 is 3. Okay? Wonderful. Okay, so now I've completed the first step of my algorithm. Okay, the first step of my algorithm, let me grab some colored chalk to illustrate this better. Okay, so the first step of my algorithm was to get a 1 in the top of this staircase here and then get zeros everywhere beneath it. Then I move down and make this number a 1 and get zeros beneath it. And then I move down the staircase one more time and make this number a 1. Okay? So now essentially what I have is I have a staircase of 1s. 1s are on top of the staircase, and then beneath my 1s are all zeros. And this is exactly REF form. So this is REF form, okay? And this is nice, but we want RREF form. So that's when I just have a diagonal of 1s or a staircase of 1s and zeros everywhere else, okay? So the next step, once I get REF, is I start from the bottom of my staircase and I work backwards. So now I start from the bottom of my staircase and I delete everything above this 1. I use this 1, I leverage this 1 to make everything above it 0. Okay? And then I'm doing the same thing for each of these 1s moving back up the staircase. Okay? So once we've achieved the REF form, we're now going to work backwards up this staircase, starting at the bottom stair, and deleting all of the numbers above it, i.e. making all of the numbers above this 1 0. Once I make all the numbers above this 1 0, I'm going to move up to this one, make all the numbers above this 1 0, etc. Now the reason why this works is because we've established these zeros underneath the staircase, they're not going to actually affect anything above them. Okay, so you'll see that when we do the calculation. So looking at this 1 here, this is already a 0, so I'm good. And then I just need to make this 1 into a 0. So I'm going to use this 1 and multiply by negative 1 and add it in to the top row. Okay, so that's going to leave the bottom 2 rows unchanged. 0, 0, 3. Now the top row, again, these zeros, when I multiply by negative 1 times 0, I get 0. So it doesn't affect the 1 when I add it in, so this stays to be a 1. Similarly, this 0 doesn't affect the 1, so this stays as a 1. Now, negative 1 times 1, negative 1 added to the 1 is 0 by construction. And negative 1 times 3 is negative 3 added into the 6 is 3. Okay? So now we're here. So we've completed this one, so now I'm going to move up the staircase to this pivot, to this one, and I'm going to use this one to delete everything above it. So in this case, I just multiply by negative 1 and add to the top row, and I'm left with, okay, let's write the bottom 2 rows first, 0, 1, 0, 2, 0, 0, 1, 3. Okay, again, this one stays unchanged. Now negative 1 times 1 added into this one is 0. This 0 isn't going to affect this 0 here. And then 2 times negative 1 is negative 2 added into the 3 is 1. So I'm left with my RREF. Okay, so the RREF is essentially when I've completed the staircase of 1s, and then every step of the staircase will have a 1 above it, and that 1 is going to have zeros everywhere else in its column. Okay? Now, we'll see in a moment when I do a more complicated example that you're not always going to get a perfect staircase like this. And we'll see that in a minute. But in this case, we have a perfect staircase of 1s. Okay? So this is called a consistent independent system of equations because we get exactly one solution. Now, if I translate this back into equation form, what this matrix tells me is that 1x plus 0y plus 0z is equal to 1. And then the second row tells me 1 times y is equal to 2, so y is equal to 2. And the third row tells me z is equal to 3. Okay, so this is translating back this matrix into the equation form. Okay, now to be more explicit, the first row of this matrix, just so you can see, the first row is 1 times x plus 0 times y plus 0 times z is equal to 1. And I've just omitted the zeros here. Okay, so this is my solution to my system of equations. Great. And there's exactly one solution. This is the only point that works. And so you could say geometrically these 3 planes that we started with 3 planes. They intersect at exactly one point, and that is given by this solution. Okay. So now let's move on to a more difficult example. I'll try to move quickly. We are going to deal with the dreaded 5 systems of equations. 1, 0, 4, 3, 1, 8, negative 3, 4, negative 8, 3, 13, and 16, negative 2, 0, negative 8, negative 5, negative 1, negative 14, 1, 0, 4, 3, 2, 9, and negative 1, 3, negative 1, 6, 10, and 21. Okay, an absolute beast of a matrix. We're gonna do it all the way through, just so I don't just do the easy examples. Okay. Now, real quickly, what does this say in equation form? Let's just talk about the equation form real quick. For the equation form of this top one, it's going to be like x1. So instead of using x, y, z previously, my unknowns are perhaps, I now have 1, 2, 3, 4, 5 unknowns. So let's say x1, x2, x3, x4, and x5. And I want to solve, I have a system of 5 equations with 5 unknowns. And these unknowns, I want to solve for them. So the first equation reads x1 plus 0x2 plus 4x3 plus 3x4 plus x5 is equal to 8. That is this first equation here. The second equation, okay, negative 3x1 plus 4x2 minus 8x3 plus 3x4 plus 13x5 is equal to 16, and so forth. Okay? I'm not going to do the other rows, but this is how you would translate this matrix into a system of equations with 5 unknowns, namely x1, x2, x3, x4, and x5. Okay? All right, so let's apply the algorithm. Aha, so we already have a 1 here. So I'm going to start here. This is already a 1, so we're already in business there. So I'm going to go ahead and use this 1 to destroy everything beneath it. Okay? So how do I destroy the negative 3? Well, I want to multiply this equation by 3 and add it into the second row. Let me be careful about this. Okay, so I'm adding it into the second row. Okay. So we have 1, 0, 4, 3, 1, 8. 3 times 1 is 3, added into the negative 3 is 0. 0 times 3 plus 4 is 4. 4 times 3 is 12, minus 8 is 4. 3 times 3 is 9, plus 3 is 12. 3 times 1 is 3, added into the 13 is 16. And then 3 times 8 is 24. Added into the 16 is 40. -2, 0, -8, -5, -1, 14. Okay. So we're here. Now, let's look at this row. It's kind of growing. Now, I want to make sure that my numbers don't get too big. So I don't have to actually, I could just move on, and the next step would just be to destroy this 2, right? But I noticed that what I got was a row that I all have multiples of 4. So this row, everything in this row is divisible by 4. So I should immediately simplify this. I shouldn't wait. I should immediately simplify this by multiplying this by 1/4, this row, okay? And that's just so my numbers don't get too big. And, if you can simplify, then why not? Okay, so 1, 0, 4, 3, 1, 8. Okay, so this row getting multiplied by 1/4, I have a 1, a 1. 12 divided by 4 is 3. 16 divided by 4 is 4. And a 10 here. Okay, and then I have -2, 0, -8, -5, with 1, -14, 1, 0, 4, 3, 2, 9, and -1, 3, -1, 6, and 21. All right. Okay, so now we're here. In the next step, I'm still at my first pivot, first step of my staircase, and I need to delete the 2 now. Okay? So to get rid of this -2, I'm going to multiply this row by 2 and add it in. All right? So this will give me 1, 0, 4, 3, 1, 8, 0. Two times 1 plus -2 is 0 by construction. That's why I chose 2 to begin with. 2 times 0 is 0. Added into the 0 is 0. 2 times 4 is 8. Added into the 8, oh, look at that, another 0. 2 times 3 is 6. Added into the -5 is 1. 2 times 1 is 2. Added into the -1 is 1. And 2 times 8 is 16. Added into the -14 is 2. The other rows all stay the same. Okay. Now I'm going to get rid of this one. So that amounts to multiplying this row by -1 and adding it in. Now, instead of rewriting the matrix, let me just go ahead and... Actually, no, I'll rewrite the matrix. 4, 3, 1, 8, 0. Yeah, so it's a good idea. You could just erase rows and I could have just erased this and then replaced it with the new one. but it's not really good when you're just first learning because you want to follow every step that you make. That way you can go back and see if you made an error and you can show all of your work, etc. Okay? Okay, so 0, 0. All right, negative 1 times 1 added into the 1 is 0. Negative 1 times 0 added into the 0 is 0. Negative 1 times 4 is negative 4. Added into the 4 is another 0. Negative 1 times 3 is negative 3. Added into this 3 is 0. Negative 1 times 1 added into the 2. Let me highlight the row that I'm doing here. Okay, so negative 1 times 1 is negative 1 added into the 2 is 1. And then negative 1 times 8 is negative 8 added into the 9 is 1. All right. Now finally, to get rid of this negative 1, I'm going to multiply this row by 1 and add it into the bottom row. Okay. 1 added into negative 1 is 0. 0 added into 3 is 3. 4 added into negative 1 is 3. 3 added into the 6 is 9. 1 added into the 10 is 11. And 8 added into the 21 is 29. All right. So that completes the first step. Yeah, it's kind of a painstaking process. Hopefully that your teacher doesn't give you this big of a matrix on an exam. Okay, so I've achieved this one and I have all zeros underneath it. I'm going to move down the staircase. I have a 1 here. I want to make this number a 1. Well, it's already a 1, so I'm good. Okay, remember how I divided by 4 a long time ago? When this was like 4, 4. I mean, this row, we could go back to, this row used to be 4, 4, 12, 16, and 40. Okay, so if I hadn't divided by that 4, then at this step of the process, I would arrive at this 4, and I'd be like, okay, I need to make this a 1. So let's multiply this row by 1/4 to make this number a 1. Okay, and then I would have gotten 1, 1, 3, 4, and 10. Okay, great. So now I need to destroy everything beneath this 1 now. Well, I already have 2 zeros, so I'm good there. So I just need to get rid of this 3. So I want to do that by multiplying by negative 3 this row and adding it into the bottom. Okay. All right, so negative 3 times 1 is negative 3 added into this 3 is a 0. This guy is 0, 0, so there's 0 here. Okay, now negative 3 times this 1 is negative 3 added into this 3 is 0. Negative 3 times this 3 is negative 9 added into this 9 is 0. Negative 3 times 4 is negative 12 added into the 11 is negative 1. Negative 3 times 10 is negative 30. Added into the 29 is a -1. Great. Now I've completed this part of the staircase, so I'm going to step down and make this number a 1. But this number is a 0, and everything beneath it is a 0. Okay? So notice if this number is a 0, there are two possible cases. Don't look at anything above this number, first of all. Yeah. Don't consider anything above this number. Because everything above the number is locked into place by this staircase. So everything above this number is already locked into place. But everything below this number I have freedom to deal with. So because these two are zeros, I can't actually do anything. However, if this number was like a 1, for example, okay, if there was a 1 below this 0, then at this point I would swap rows. So I would swap these two rows, and by swapping the two rows, I would end up with a 1 in the place that I needed, okay? However, this is a special case where there are only zeros beneath my 0. So there's nothing I can do to get this to be a 1. There's nothing I can do. Remember, I can't deal with anything above this, and there's nothing I can do with these bottom two rows to get this into a 1. So what do I do? Well, this is a non-perfect staircase. So I just keep moving along the staircase. Okay? This is very important to understand. So if I just have zeros with zeros underneath everything, I can't do anything. I have to move on to the next stage of the staircase. And now I want to get a 1 here. Okay? So I have a 1 there, and actually I already have zeros underneath it. So I'm in good shape here. So this stage of the staircase is already completed. So now let's move down. And now I'm here on my staircase. I have a 1. I need to delete everything beneath it. So that just means getting rid of this -1. So I multiply this by a 1 and add it in to the bottom row. Now, this one I'm going to afford myself the ability to just rewrite this matrix, okay? I'm not going to rewrite the whole thing. So 1 times 1 added into this -1 is 0, and the same thing is for this one. This 1 times 1 added into this -1 is 0. So when I perform this row operation, I get zeros, okay? Great, and now I try to step down once again, and I'm at a 0, there's nothing I can do there, so I've completed my staircase. Okay? So let's just take a step back and recognize, okay, this is the REF. REF means I've completed a staircase, which means I have 1s at each step, and then each step down, when I step down, I better have a 1 followed by zeros. And if I don't step down, if I move across, then every time I move across, I need to have zeros everywhere underneath me and a 0 on the staircase. Okay? With the REF in play, I can now work towards getting the RREF. Okay? So the RREF is I consider my staircase and I look at the pivots. The pivots are the 1s. Okay, why are they called pivots? Because we're kind of using them to destroy other things in the matrix. So they're kind of pivotal in that sense, right? I don't actually know why they're called pivots, but that's why what I think of. So this guy, this 1 is one of my pivots, okay? And I can use it to destroy everything above it. Similarly, this one I'm going to destroy everything above it, and this one I'm going to destroy everything above it. Okay, so destroy everything above it means make all the numbers above it 0. Okay, now I can't use zeros to do that, so these are kind of useless. I can't do anything with these zeros. I'm going to leave them be, and I'm only going to use the 1s on my staircase. So beginning with this 1, okay. Now, why am I beginning with this one? I begin at the bottom of the staircase. Notice I built the staircase from the top down. I built the staircase starting at the top left corner and moving down. However, that gives me the REF. The next step of the algorithm to get the RREF, once I have my staircase built, is I move up the staircase, back up. okay, so this is essential, is that I start now at the bottom with this one, my first one at the bottom of the staircase, and I destroy everything above this one. Okay, so I need to make this one into a 0. So I multiply this by -1 and add in. Okay, 1, 0. Okay. So, okay, I started to write the row, so I'm adding this one, this -1 times this row into this row. Notice that the zeros, these zeros are not going to affect anything above them. So everything, this 0, 0, 0, 1 will remain the same. And then I have -1 times 1 added into this one is 0. And -1 times this one is -1 added into the 2 is 1. Okay? And a row of zeros. Now, if you get a row of zeros like we have here, doesn't mean you did anything wrong necessarily. That's actually okay. It just means that one of the equations was redundant, and I'll speak about that once we finish the problem. Okay, so now I need to use this one to destroy the 4. All right, so I multiply this by -4 and add into this row. Okay. All right, the zeros aren't going to affect anything. So again, this 0 times -4 is 0. When I add, I'm just adding 0. So all of these numbers will be unaffected. 0, 1, 1, 3, because this row operation is just adding a 0. And then here I have 1 times -4 is -4 added into the 4 is 0. And 1 times -4 is -4 added into the 10 is 6. All right. So, making progress. My last thing that I need to delete above this 1 is this 1 in the top row. So I multiply by -1 and add it into the top row. So -1 times this row added into the top. These zeros will not affect the 1, 0, 4, 3, since I'll be adding 0. Then this is -1 times 1, which is -1 added into this 1 is a 0. And -1 times 1 is -1 added into the 8 is a 7. And like most teachers, I'm going to not follow the advice that I give to my students, and I'm not going to rewrite it every time, just to save you all a couple minutes of your life. Okay, so now we've completed the first part of step 2, moving back up the staircase, started at the bottom pivot and deleted everything above that pivot. So now I'm going to walk up the staircase and arrive at my next pivot, and then delete everything above this pivot. Now it's critical that you do it in this order, okay? It's critical that you delete down starting at the top of the staircase, but delete up starting at the bottom of the staircase, okay? If you don't follow this chain of steps, this algorithm won't work, okay? So let's use this one to delete everything above it. So that means multiplying this by a -3 and adding it into this row. Why do I choose -3? Well, because I want this 1 to delete the 3 when I add it in. So I have to multiply it by -3 to to do that. Okay, so these zeros won't affect anything above them. So these stay the same, 0, 1, 1. Now, 1 times -3 is -3. Added into the 3 is 0. This 0 isn't going to change anything. Then 1 times -3 is -3. Added into the 6 is 3. Okay. Next, I'm going to delete this 3. Same idea. Multiply by -3. Use the pivot to delete the numbers above it, and multiply by -3. Add it in. Okay. These zeros aren't going to affect the 1, 0, 4. The 1 times -3 is going to kill this 3 and make it a 0. 0 times -3 won't affect this number. And then 1 times -3 is -3. Added into the 7 is 4. Okay? All right, so now I've completed destroying everything above this pivot, so now I step up the staircase. Now I arrive at my next pivot, and I delete everything above this, right? Okay, wrong. This is incorrect, okay? Incorrect. Remember the staircase. This one is not a pivot. The staircase looks like that. Okay, there are actually no pivots in this column, so I actually cannot destroy information in this column. There's nothing I can do here. The pivots that I'm going to destroy are the ones sitting on my staircase. The ones sitting on the steps of the staircase, those are the ones that I use to delete everything above them. Any row with a 0 sitting on the staircase, i.e. row with no pivot, I leave alone. Okay, so I move back up the staircase to the next pivot, 1, and I delete everything above this one. Well, I'm already good because it's deleted. So this is already a 0, so I'm good. So we have it. We're done. We have the RREF. So let me just polish this off here. Okay, so this is the RREF. And now we need to write the solutions in terms of the unknowns x1, x2, x3, x4, and x5. So basically, once I obtain the RREF, I need to translate it back into equation form, okay? So how do I do that? Well, essentially, every column that doesn't contain a pivot is going to contain a free variable. Okay, so notice that I have this column with no pivots, so that'll be a free variable, and I have a row of zeros. The row of zeros is essentially a sign that you have a free variable, right? If you have a row of zeros, then what that means is that one of your equations, that you were initially given 5 equations, turns out one of them was redundant. So they weren't actually 5 meaningful, there weren't 5 pieces of information, there were really 4 pieces of information given 5 equations. So one of those equations you didn't even need to begin with. It was irrelevant. It's like if I gave you x plus y plus z is equal to 10, and then I also told you that 2x plus 2y plus 2z is equal to 20. Well, these two equations are the same thing. I just multiplied the first equation by 2. So these two equations are really one piece of information. They're not actually 2 independent equations. So these are called dependent equations, or consistent dependent equations. Okay? So in this case, I have a set of dependent equations. I have 4 independent equations, but my total set of 5 equations is dependent. Okay? All right, so let's write this in equation form. Starting with the bottom row, I have, remember my variables, I have x1, x2, x3, x4, and x5. So this bottom row tells me x5 is equal to 1. Now, not the bottom row, but the fourth row. Now the third row tells me x4 is equal to 1. Do you see how I'm getting this? So this is just 0 times x1 plus 0 times x2 plus 0 times x3 plus 1 times x4 plus 0 times x5 is equal to 1. So that just means x4 is equal to 1. That's this row translated. Let's translate this row. This row says x2 plus x3 is equal to 3. And the final row says x1 plus 4x3 is equal to 4. Okay, so I have 4 independent equations, and they're in simplified form. So let's write this in a better way. So maybe leave the matrix up. I'll write it over here. Hopefully y'all can see my writing over here. So I'll write x1 plus 4 x3 is equal to 4. x2 plus x3 is equal to 3. x4 is equal to 1. Is equal to 1, x5 is equal to 1. Okay, so now I'm going to use a little trick that they probably tell you to do, and they don't really explain it. So what I'm going to do is that I look at the column. Okay, so I look at this column. It's the column without the pivot. It's the column without the pivot, okay? This is corresponding to my free variable, x3. So the column without the pivot, I write a redundant equation, x3 is equal to x3. This is the completely useless fifth equation, corresponding to the fact that the 5 equations we were given with to begin with, actually one of them was useless. So x3 equals x3 is a useless equation, and we only write it to let people know that I'm going to express my final answer in terms of x3. So x3 is a free variable. What that means is that x3 can be anything. You can give me any x3 that you want, and I can give you a solution, x1, x2, x3, x4, x5. Obviously, your x3 you gave me, but I can give you the x1, the x2, the x4, and the x5 to give me the solution, okay? So what this means is that for any x3, there is a solution, let's call it x3 star. So if you give me an x3 star, then there exists a solution x1, x2, x3 star, x4, x5, okay? So basically I have a family of solutions, and they're all depending on x3. A lot of my students get confused with this point. The idea is, okay, to say it in one sentence, we're going to express our solutions in terms of x3. All right? So how do we express our solutions in terms of x3? Well, I just write I bring x3 over to the right-hand side. So I write x1 is equal to 4 minus 4x3. x2 is equal to 3 minus x3. x3 is equal to x3. x4 is equal to 1, and x5 is equal to 1. Okay? So this is my boxed solution that I turn in on the test.